In this paper, we present a field optimization-based process planning method for hybrid manufacturing. Topology optimization considering manufacturability constraints, such as self-supporting, often has to sacrifice certain mechanical performance. Differently, with the help of hybrid manufacturing, such constraints can be removed to obtain better results. Existing voxel-based method has limitations in 4 aspects: poor scalability according to voxel's resolution, lack of optimization for the determined process, uncontrolled distortion on intermediate structures, and discontinuous toolpath with frequent jumps. All these challenges can be overcome by our field optimization-based framework. Given an input shape, after applying an optional pre-processing step for adding removable support, its signed distance field is constructed. 5 neural fields are employed for process planning. The AM sequence field and the AM occupancy field jointly determine where and when material deposition should be applied. Similarly, the SM sequence field and the SM occupancy field determine where and when the already printed materials should be removed by subtractive operations, such as milling. The cutter configuration field defines the center position and the tool orientation of the cutter. Based on these fields, the states of intermediate structures can be obtained at any timestamp. We then employ finite element analysis to estimate process-induced distortion. The optimization objective combines several loss terms, including shape completeness, support volume, distortion, self-supporting, and collision-free. The neural fields are optimized through backpropagation, while Bayesian optimization is adopted to determine the best weights. After that, in the post-processing phase, manufacturing layers are first extracted based on the optimized field. The toolpaths are generated thereafter. Here, we compare our method with the voxel-based method. The voxel-based result contains frequent tool jumps, while our method gives more continuous and smooth motions. Our method also significantly reduces workpiece distortion. This shows the state that gives the largest distortion from our method. This is the intermediate structure giving the largest distortion from the voxel-based planner, where the distortion is much larger. As our method has explicitly minimized the volume of extra supporting structure, the manufacturing sequence generated by our method can finish much earlier. The histogram of distortions on intermediate structures clearly demonstrates the advantage of our method. Here shows the physical fabrication process of the GE bracket model. Here shows the results of other models fabricated by our method. Models with high complexity in topology can be fabricated successfully. Thanks for watching.